Today, we're moving into this area which, for most places in the world where they teach calculus and they have 2 semesters, there's a dividing line between the first semester and the second semester. And because of the way they do things here at USF, today's kind of that dividing line. We're going to start looking at something called an antiderivative, which again is usually part of the second semester. Not really sure if it's because we eliminate stuff the first semester or we crowd things in or we're more efficient, but that's the way it is. So I'm going to kind of sneak up on what this idea is about. Imagine, we're doing this example we talked about at the beginning of class. We're driving somewhere in a car. This is an art class, fortunately, we're going to be first. And, as this is the front of the car, and you're watching little mile markers go by. 1, 2, 3. And you calculate an average velocity, right? Velocity equals distance over time. If you keep track over much shorter distances, you can kind of simulate what your speedometer does, right? So, yes?
I was just wanted to ask if this was part of the midterm test.
You wanted to ask what?
If this was part of the midterm,
Okay, I announced it a couple times, but no. Today and tomorrow are not part of the midterm. Last Thursday, last Tuesday, everything from the beginning of class could be part of it. Yeah. Good question. Okay, so we can from measuring distance, we can get velocity, and we have a name for that. We call that differentiation. That's what we've been studying. But if you're in a car, maybe it's an auto-driving car and the windows are all dark. Or, but you can see the speedometer. And if you watch the speedometer and you keep track of intervals of time, you can figure out what the distance is and add up the little distances. You say this distance is velocity times time. So you can kind of read this backwards too. As a very simple example, if your velocity was a constant, then your distance would just increase linearly. This is distance, and these are both time. So again, here we've learned how to take something more complicated than this, but here it's a straight line. We find the derivative. Derivative straight line is a constant. We have a constant. But likewise, here we can intuit that if we're going at a constant velocity, at least, the distance just increases linearly. really early here is, I kind of started us here, but that might be a piece of information I know, but I might not know where we're starting. That can be a problem. Just knowing velocity doesn't tell me where we started. It just tells me, if I know where we start, how far we've gone. So, since going from here to here is differentiation, we're going to, for the time being, give the name of going from the velocity to the distance as antidifferentiation, or finding an antiderivative. So, in general, this can be an arduous kind of task. However, in many cases, we're going to find it really easy because we know differentiation. All right, so I'm going to give you a simple example here. We have some function f of x equals x, just a simple line. We want to find its antiderivative. Well, we think about the power rule. The power rule says the derivative of x to the n is 10 x to the n minus 1. So we figure we're going backwards. Like we found the derivative, we subtract 1 from x, we probably have to add 1. So we look at provisionally some function x squared. Just a guess of what the antiderivative might be. And we find the derivative. Well, g prime of x, of course, is 2x. Well, that's not what we wanted, but it's pretty obvious now how to get what we want. If we start instead with, now I'm going to write it as, this is very typical notation, using a capital F to mean the antiderivative f of x. If we start with x squared over 2, and we find its derivative, sure enough, it's just what we wanted. So that's it. We get a lot of antiderivatives for free because we already know a lot of derivatives. We just have to kind of look at what we know and work it backwards. And again, hopefully just have to modify a constant here. In this case, we add, we replace this with a half. All right, let's take another example. We have the derivative, we have the function sine of x. And we want to find its antiderivative. Well, again, an obvious candidate is cosine of x. At least that's a good guess to start with. We take a look at its derivative. The derivative of cosine is the negative sine of x. Oh. Well, that's almost what we want. But, here we can see if we start with negative sine of x, that its antiderivative is just going to be, wait a minute, hold on, negative cosine of x. That if we find the derivative of the negative cosine of x, well, the derivative of the cosine is the negative sine, so we added a sine, so we're just going to end up where we want to be. Sine of it. Alright. I'm going to try this all over. I'm confusing myself. we wish to find the antiderivative of sine of x. We try cosine of x, and we find its derivative is negative sine of x. We're just have a factor of -1 here. So we conclude that if we take cosine of x, put a negative sign in front of it, finding its derivative, we will get back to the sine of x. I think I said that a little better the second time. Is any question about this? It's pretty straightforward. It's just you take something you know, and you kind of you're working it backwards now. All right. I'm going to come back to this problem here, where I don't know where I started, and address it a little differently. I want to look at two functions here. So I look at f of x equals x squared minus 2x, and g of x equals x squared minus 2 of x plus 3. Well, again, at the risk of offending people with any artistic aesthetic here, I'm going to try and just do this freehand. So this is my f of x. And this is my g of x. And in spite of the lack of perfection in my drawing, these both look exactly the same. They should. They just differ by this constant 3. This function moved up 3. But when I look at their derivatives, what do I find? I find f prime of x is 2x minus 2. I find g prime of x is equal to 2x minus 2. They're the same. Well, it makes sense because at any x you are on the graph, you try and draw a tangent. That tangent is going to have the same slope on either graph. So the conundrum we have is when we're doing antiderivatives, there could be a constant involved that we don't necessarily know what it is. So if we're asked to find the antiderivative of either of these two, instead of a specific one of these functions, we get f of x equals x. You know what? Anybody's watching, I should have been 3. That should have been squared. So we get x cubed minus 2x plus some constant c. Unknown, we would need additional information to figure out what this constant is. In the case of the driving example, if you know where you start, then you know what the constant is. So this is an issue that we have finding antiderivatives, that if we don't have any additional information, we don't get a function, we get a family of functions that there's a constant, an unknown constant in there. Now, an example of the kind of information that would help us out here would be, well, what if we know that f of 0 is 5? Well, that's all we really need to know. 5 equals 0 minus 0 plus c. Aha! In this example, my c would be 5. And in many problems involving antiderivatives, we're going to find just that. That you have some starting point or some anchor that will tell you about the c. Okay, any questions about this right now? We're gonna do a lot with this today, but before we do, I'm going to go off in a wild digression. Everybody happy with this so far? Okay. So I suspect that most of you weren't expecting today discussion on graduate level astrophysics. But, there we go. You may have heard something called Einstein's theory of general relativity. His special theory is general theory. And this is a theory of gravity. You got the sun and the earth. And before Einstein, we had Newton's theory of gravity, which just said, massive objects pull each other with this force called gravity. Nobody really knows, what that means, how that works. But they don't know how electrons and protons, positive and negatives, attract each other, or how positive north poles and south poles of magnets pull each other either. But Einstein came up with a theory, and I'm just going to write the basic version of that theory to you. It's an equation, and it looks kind of like this. And I'm going to tell you a little bit about what this is about, even though it won't be on the final. Okay. So we got a G with a subscript of 2 Greek letters, another Greek letter, and then G with 2 subscripts, and then this is not a K actually, it's a Greek letter, and a T and another couple subscripts. Well, turns out this is just this really, really compact way of writing this theory. I'm not going to go into really any of the details, but this actually represents 256 equations. Each of these letters here represents x, y, z coordinates, and t. This guy actually is a constant. We're going to talk about him. And basically, what he's saying is that the shape of space and time is kind of mitigated by the mass and the energy within that space. Okay, this is not important. I want to talk about this thing here. It's a constant. It's called the Cosmological Constant. And you may have heard of it. Supposedly, in the original equation, Einstein left it out. and then he put it in. And then he was later heard to, supposedly say this mistake was his greatest blunder. Now, the reason I'm bringing all this up is this idea here of a constant of integration. That's what the cosmological constant is. It's a constant of integration. When you develop these equations, all of a sudden you're doing an antiderivative kind of operation, and then there's some unknown because you don't know where you're starting. Well, for many years, Einstein kind of got his way. People just assumed this was zero. It doesn't apply. But in 1998, here we are in the center of the universe. It's kind of a weird thing that every place in the universe is the center of the universe. And looking way, way, way out at things moving away from us and everything else, some scientists did a measurement on a certain kind of supernova. Supernovas, a star explodes and gives a lot of energy off. And by figuring out, the brightness of these supernovae, and also using something called the redshift, which tells us how fast they're moving away, they discovered that not only is the universe expanding, which we knew, but it's accelerating. It's moving away faster and faster over time. And while we don't know the physics of why that's happening, we give that a name, which you've probably heard. It's called dark energy. This unknown energy is pushing everything away faster and faster. This cosmological constant, well, you can measure it, and as far as the equations work, it completely fits in, it completely explains it. So, I hope that was fun. There's a message here. It's a very small message. The message is that these constants are important. They can be, they are important. All right, that was fun. Okay. So when your parents call up this weekend and say, what did you learn today, this week, we can say, well, I learned about Einstein and special relativity, cosmology. That'll help them feel like they're doing the right thing by sending them here. All right, all right. Let's look at the antiderivative of x to the n. So, because of what we know about the power rule, we suspect, this is our f of x, we suspect our antiderivative is going to look something like this, x to the n plus 1. We know when we find its derivative, we're going to lose an x. So we find the derivative here, and it's, of course, n plus 1 times x to the n. Well, if we look at x to the n plus 1 times x to the n, and compare it to what we started with, and we realize we're going to have to modify this. So here, clearly, when we find the derivative of x to the n plus 1, right, we multiply it by n plus 1, which divides out, and we just have x to the n, which is what we want. So this is our, we call this our inverse power rule. From this, if we had a more general polynomial, a to the n x to the n plus a to the n minus 1, the n minus 1 plus a1x plus a0. Well, if we want to find the antiderivative of this, we can just apply this rule here. We're going to get a to the n x to the n plus 1 over n plus 1 plus a to the n minus 1 over n to the n. So forth. We're going to get down here a to the 1 x squared over 2 plus a naught x plus, you're going to see me try and be very consistent about this, and some unknown constant of integration. So here we have a formula, and now we can find the antiderivative of every polynomial just by using that formula. All right, so but there is some problem with this, though. Let me see where we might have a problem. The reverse power rule. Some places it's going to fail. Yeah. Yeah. What happens if n is -1? Well, that would be equivalent to f of x equals 1 over x. Well, I'm going to leave that for a moment. We're going to come back to it. But clearly, the power rule doesn't work here. Yeah, x to the minus 1. So we'll have to think about what the antiderivative of x to the minus 1 is. Okay, let's use this strategy, and again, let's kind of develop a table here. So we have functions and their antiderivatives. And we decided x to the n, if n is not -1, it's going to be x to the n plus 1 or n plus 1 plus c. Now, who wants to take an easy stab at this one? E to the x. What's the antiderivative of e to the x going to be?
E to the x plus c.
I think we already did sine of x. That's negative cosine of x plus c. So we want to fill this out a little. Sine of x, cosine of x You know, another way to think about this, something looks pretty simple, is you can say to yourself, what function, when derived, you find the derivative gives us this? You want to throw something out? Yes?
Sine of x
Sine of x.
plus c.
Like the way I feel like I'm training people there. Yes. Right. There's a C. Okay. What we're not going to do here is we're not going to go through and say tangent, secant, cosecant, cotangent. We're only interested in things that we kind of already know. We'll get to these at some point. So I say secant squared of x. Anyone recall what you find the derivative of to get secant squared? Yes?
Tangent
Tangent?
of x plus c.
Okay. Secant of x times tangent of x. Remember this one? Yes?
Secant squared of x plus c. Secant squared of x.
Close. It's just the secant. Let's try that. Secant is 1 over the cosine, right? Or cosine is -1. So we use the power rule and the chain rule. -1 cosine of -2 times derivative of the cosine negative sine. Negatives cancel. We have sine over cosine squared, sine over cosine, times 1 over cosine, so tangent times secant. So it's just a secant. Secant squared is what you get from the tangent. All right. Down memory lane here. Anyone recall antiderivative of 1 over square root of 1 minus x squared? We've actually seen this. I want the derivative, I want the antiderivative. This is something, you know, you might want to have on that cheat sheet. What can I find the derivative of? Let's get this. All right, well, good to know this in both directions. This is the inverse sine of x, or the arc sine, plus constant. You know, knowing that will help, but 1 over, function 1 over 1 plus x squared. Anyone recall that could be? All right, well, you probably want to review these. Not the antiderivative part, but the derivative part. This is the inverse tangent of x, of course, plus c. And I have two easy ones. One, call the what function I can find the derivative of to find the hyperbolic sine of x. Did a day on this. It's getting cold in here. Well, okay. remember there are these functions that they work with differentiation much nicer than the sine and cosine. Derivative of the hyperbolic cosine is hyperbolic sine, and it goes the other way. Probably would be useful to recall that the hyperbolic sine can just be written e to the x minus e to the minus x over 2. Hyperbolic cosine e to the x plus e to the minus x over 2. And I think you can figure out the hyperbolic tangent from that. All right, so we've got, little table of useful antiderivatives. We can apply these directly. If I said, well, what's the antiderivative of e to the 2x? Well, you can, use that process I gave you. You say, well, it's e to the 2x times, well, the chain rule says 2. So if I start with half e to the 2x, when I find its derivative, I'll get back to what I'm looking for. And again, you can use these in a similar manner. I think where we're back, though, is we want to look at this guy again now. F of x equals 1 over x. So we're looking for some function x, f of x, whose derivative is 1 over x. Anybody recall a function whose derivative is 1 over x? Which we had one. Yes?
Actually, natural log.
Yeah. There's a catch here. The log of a negative number is undefined. So, this can only be true for 0 to infinity. Maybe a little diagram would help here. So log of x is the log of 1 is 0. It's going to kind of go like this. And its derivative is going to go like this. But 1 over x also, this function isn't limited in this way. This will be its, it's not limited this way. Is there anything we can say about the derivative of this guy? Seems like as you go to negative infinity, it's going to 0, but where is it coming from? It's coming from a negative slope, right? So it's negative going to 0. This guy, he's going out, he's also going to 0, but from positive. Over here, as we get close to 0, the slope gets close to infinity, but from a negative side. But here, we're getting close to. Wait, is that right? No, that's negative. We're also. The thing you want to see is that the derivative of 1 over x, the derivative of log of negative x is just derivative of the absolute value of the log of negative x is just 1 over x. Derivative of the absolute value of x is 1 over x. That is, if you take the derivative of this and you find its absolute value, you're going to get the same derivative as you have here. So, as a general rule, we want to write this. We want to write this way. The antiderivative of 1 over x is the log of 1 over the absolute log of the absolute value of x. If x happens to be positive, the absolute value is redundant. You don't need it. But you can find the antiderivative of this function in the negative area. It just looks like this. Okay. All right. It's time for a 5-minute break, and then we'll come back and we're going to learn a little more about antiderivatives. Daniel's not here, is he? Anybody who wanted to write this down has it down. We're going to move on here. We may use some of this. Okay, so we're back to working with this process that we're going to find important, which is undoing what we learned at the beginning of the semester, how to find a derivative. We're trying to find an antiderivative, the function that our derivative came from. We have a few examples of things we learned because of things we already know. We want to go a little more flexible, and so we want some rules that we can follow that will help us in this process. I've already kind of snuck in some because they were so obvious, but I'll be specific here. So we know that the derivative of a function, of a constant times a function, we use a little c here, is just equal to that constant times the derivative of the function. That is, constants move in and out. So if we want to find this antiderivative of some function we want to find the antiderivative of this. The constant doesn't matter. That constant that we're multiplying by, we still need our big C can always be part of the antiderivative. Similarly, you know, if we have the derivative of the sum of two functions, well, that's just the derivative of each function separately. It's our addition rule. So that tells us if we have the sum of two functions that are derivatives, that their antiderivative is just going to be, I can write it, f of x, g of x. It's just going to be their sum. Of course, plus a constant. Now, we can gain a little leverage here using the chain rule. If we see something that looks like this, well, let me start the same way I'm doing this here. If we have some function raised to some power, raised to power here, and we find its derivative, well, we know from the power rule, it's n f of x, the n minus 1, but times the derivative, that's the chain rule. So if you see something in this form where you see some function f of x to some power times its derivative, this ought to give you a hint on how you can find its antiderivative. Its antiderivative is going to be f of x to the n plus 1 over n plus 1. Okay. How does that work? Well, when you find the derivative, you multiply n plus 1 times f of x, and then you drop 1 from the exponent. But now we've divided out the n plus 1, and now you have to multiply it by the derivative. So that hits you back to this form. So this is kind of a neat trick if you happen to see something that looks like this. Some function, either, this could be a 1, right? Right? But some function times its derivative, we can kind of undo differentiation using the power rule, keeping this in mind. Okay, let's just do an example of that. Say I have some function f of x equals sine of x cosine of x. Well, if you think about that, that's like sine of x to the 1. So if I'll give it a try here. Sine squared of x over 2, what happens? To find its derivative, it's going to be 2 times sine of x. That's going to eliminate the 2's, times the derivative of the sine, which is the cosine. Gets us back to where we want it to be. Oh. Don't want to forget the C. You know, this is I find this kind of interesting because I know that sine of 2x is what? 2 sine x cosine x? So these are the same. So the question is, can I find the antiderivative of this? If I do, will I get the same thing? So just going to leave that out there for the moment. Actually, it's kind of interesting. All right, so, you know, with this, I guess my first guess might be something like cosine of 2x, right? Maybe negative cosine of 2x over 2. That's my first guess. So I want to find the derivative. Derivative of the cosine of 2x, of the negative, of the cosine of 2x is the negative sine. So my sines are going to go away. So I'm going to get sine of 2x over 2 times 2 because of the chain rule. So now I come to the conclusion that my antiderivative is sine of 2x plus c. Oh, wait, what did I get before? Sine squared x over 2. It seems like a conundrum, doesn't it? I just kind of went about something by a different path, and it looks different. Can anyone see why these really aren't different? All right, I'm going to leave that for later. We'll get back to that. All right. Another formula or pattern you want to look for has to do with the fact that you find the derivative, the log of some function or absolute value, you're going to get 1 over the function times the derivative. So that tells me if I see this pattern, derivative of some function over the function, and I want to find the antiderivative, this is going to help me. So I think this is best done with an example. My function is x over x squared plus 1. Well, I don't quite have this yet, right? I could change this. I could make this 1/2 2x over x squared plus 1. That would give me what I want, all right? Derivative of a function over the function. Clearly, derivative of x squared plus 1 is 2x. So the antiderivative will be log of the absolute value of x squared plus 1 Well, you can see right away I can get rid of those absolute value signs, because this has to be positive. To the 1/2, well, what's that? That's the log of square root of x squared plus 1. What's the constant? We're going to take a look at that, how I did that. It kind of looks tricky, but we're going to see some stuff like this all quite a bit, where again you find derivative of function over a function. Okay. All right. Everybody, I want you to do a simple example for me. F of x equals x minus 1 times x plus 2. Just take some paper and try and find the antiderivative of that. Okay, who wants to suggest a first step? First step. Yes?
I boiled it.
Boiled it. Aha. This is so dumb, things that pop into your head. When I was growing up, there's a cartoon called Dudley Do-Right. Is that still around? Well, the bad guy would always say, curses, spoiled again. There we go. Okay, so that would be x squared minus 1 plus 2, so just plus 1 minus 2, okay. All right, thank you. Someone else? What next? I guess the rest of the problem. It's a polynomial, right? We could use that polynomial formula. first term, what would that be?
The x to the third over root.
Okay. Somebody else want to tell me what the next term is? Yes?
X squared divided by
Okay. I'm gonna put in a minus here. What about the next term? Antiderivative of a constant is just what? Constant times x. Okay. Am I done? No, not quite done. What did I leave out? Yeah. Got a hand signal for the back. Constant. Okay. All right. That one's should be pretty straightforward. This next one, I want you to think about it. When you see the answer, you'll go, oh, duh. But until you see the answer, you might have to just have to trust me that we've looked at how to do this. This is my function. How do I find the antiderivative? All right, any thoughts on this? Anything that you think might help? Yes.
2 over 3 minus x 2 over 3
2 over 3.
times parentheses x minus 1 parentheses x minus 1 over 3 over 2. I mean the power.
What's the power?
3 over 2.
Oh, okay.
And then erase that one. Plus C. Plus C.
Let's see. Okay. Well, let's just check first, right? That's easy. So 3/2 times 2/3. X to the minus 1 to the 1/2 times the derivative of x minus 1, which is 1. That's right. Okay. Can you give us a hint on how you came up with that? Because it's right, so you must have. I mean, if you plugged it into your
So,
computer and it told you, that's okay too.
I changed root into x minus 1 to the 1 over 2 power.
Okay.
And then I got the exponent and then plus 1 and then flipped it
Yeah.
to make it come.
Okay, so everyone see, this is, you can use the power rule here. The only thing you have to watch out for is, you're gonna have to have the derivative of what's in here, right? The f prime of what's in here, but that's just 1. So you're home free. So you can just use the inverse power rule here. So it's really quite easy if you kind of can see past that. This next one is similar. That's a big hint. How about finding the antiderivative of 1 over square root of x? Someone want to suggest how I go about this? I mean, I don't think it's at this point a big hint. This is x to the negative 1/2. Since the derivative of x is 1, just use the inverse power rule, right? How would that work? So this would become oh, 1/2 or square root of x over 2. No, that's not right. 1/2 goes here. Well, that doesn't help any. Oh, yeah, it does go here. So it's there. Okay. There we go. Plus C. The nice thing about these is that we have a skill we've honed that allows us to check. Right? This is 2x to the 1/2. Well, the c is going to go away when I find the derivative. So 1/2 times 2 is 1x to the negative 1/2, which is, of course, 1 over x. This is where I started. Okay. There's a certain way that math teachers like to scare people. They show them something that looks ugly and scary, but we're just playing around, so it's all right. This is not an exam. My function is e to the x plus 20 over 1 plus x squared, and I'm going to add a little to this. I'm going to tell you that the antiderivative at 0 is minus 2. So why don't you see if you can find the function. Before we go ahead and solve this, anyone want to just tell me what constant they got? We'll get to checking it in a minute. Anyone want to volunteer a constant term? Uh-oh, we need more time. Okay. One more time here. You have a question? Tony, do you have a constant? No, you just gave up. Okay. All right, who here thinks this is a hard problem? Okay, that's honest. Okay. It's not a hard problem, trust me, it's a scary problem. It's got stuff we haven't, we talked about, but we haven't really looked at. All right, so what's the first step? I want to find an antiderivative. What's the first step? What's the antiderivative of e to the x? See, that could have been easier, could it? Not great. Not only is the derivative of e to the x, it's antiderivative. Well, there's a constant out here. We'll get to that. Okay, so I guess this is the hard part, right? Anybody jot down that? Yes?
Would it be 20 times tan to the negative 1 x?
Yes. Can you explain how you came up with that? I mean, I'm just trying to help the other students who are having trouble with it.
No, yeah, it's essentially 1 over 1 plus x squared is tan to negative 1 of x.
Yeah.
And so just move the 20.
20. Okay, plus tan inverse x. Okay. How about the rest? Has anybody got a C yet? Is that hard too? Maybe because we haven't done it yet before. This is the information we have. F of 0 equals -2. I bet I know what's scary about this. I don't think it's, see, F of 0 equals e to the 0 plus tangent inverse of 0 plus c equals -2. I'll bet everybody knows that e to the 0 is 1. So that means that you looked at this and some of you looked at this and got scared. So just think about it. This is the inverse tangent. So we want to know what angle has a tangent of 0. Gosh. So let's see. My tangent is my opposite over these bases. Right?
Yeah, it's still correct.
That's an O. Not a 0. So as this ratio, this angle gets down here, right? It's very, very close. It's really small. What's happening to theta? It's getting small. Sine of theta or cosine of theta, tangent of theta. When is the tangent 0? What's theta? Yes? 0. It's 0. Yeah. Okay. You don't have to raise your hand. I'm just wondering. Does anybody want to? That kind of threw me. Tangent inverse. All right. All right. Well, calculus. We assume you know all that trig. Okay. So I got 1 plus 0 plus c equals -2. For c equals -3.
Professor?
Yes.
If this were like a question that you gave us on the midterm, would you give us f of 0?
I heard most of your question.
If
This will not be on the midterm.
Oh, so like on the final then?
This could be on the final, yes. And what was your question? If
Would you give us f of 0 so that we could find c?
I might, that would be a valid question. It'll be in the homework.
Okay.
Questions like this. We're going to do another one, right? Except we're going to ratchet it up. We're going to ratchet it up a bit. Here, instead of giving you the derivative, of a function, I'm going to give you the second derivative of the function. And I want to find function without any constants, but I'm going to give you two pieces of information. F of 0 equals 4, and f of 1 equals 1. And you'll find, when we're done, there are going to be two constants, because we have to find the antiderivative twice. And you'll find that two pieces of information generally is adequate in this function now. So get that elbow working. All right? Yes.
So what happens there is that let's go for the first one, kind of get the antiderivative second.
So you may know this, that you have to find this, right?
Yeah.
And then you have to find this. So once you found this, then you can use this. Does that answer your question?
Yeah.
Okay. All right, let's start with this. Someone want to give me a hint here? Help me out. any derivative of 12x squared plus x minus 4. Well, how about the first term? Right? It's going to be x what? Cubed. And what constant am I going to end up with? I've got 12, but what do I have to do? Divide by 3?
4.
4. Okay. How about this next calc?
3x squared
3x squared minus 4
4x.
plus c. Okay, we've done that. But now we have to do it again. Someone else want to take me through this? 4x cubed, that antiderivative is just,
X to the 4th.
thank you, x to the 4th.
X to the
Antiderivative
cube.
of 3x squared is
X to the cube.
cubed minus
2x squared
2x squared plus
cx
cx
plus alpha.
alpha. Okay. Some other letter, some other constant. I apologize. I like your alpha. I love Greek letters, but I'm just going to call this D. Excuse me. So I want to know what C and D are, right? How can I figure this out?
Plug the F0 and F1.
Okay, let's do f of 0. What's that? It's
D.
0 plus 0 minus 0 plus 0 plus d equals 4. Well, that's pretty clear. I'm just gonna put a 4 here. 1 is 1 minus 2 plus c plus 4 equals 1. Okay, well, these cancel. C equals minus 3. So, you know, takes some work, but, you know, we all know how to do this. All right. Few wind-up remarks. At the moment, this may sound like some kind of juggling match here, where, or if you like one of those movies where sci-fi movies where things are going forward in time and then you have to go backwards in time, right? You can find a derivative, so you have to undo it. There's a certain amount of, kind of mental, in athletics they call it muscle memory. But the muscle here is your brain. You have to practice this a little. There's some homework. This is going to turn out to be really a useful skill. We're going to have to add on to it some additional knowledge. And so, take it seriously. I'll put up the homework assignment after class. It's going to include a very, 2 problems that you don't need to do until after Thursday. So, play around with the homework. If you have questions, bring them in on Thursday. And that's it for today. Thank you.